Problem 3. Here we have a uniform electric field of magnitude equals to 325 V per meter is directed in the negative direction. Uh, the coordinates of point A, minus 2, x equals to minus 2, minus 0.2, and y equals to minus 0.3. And the coordinates of B equals to 0.4 as x and y equals to 0.5. Here we have x and here we have y. Okay, I want to calculate the electric potential difference VB minus VA using the blue path. Okay, here you can go from A to B through the point C. Okay, let me explain before the problem. In general, in order to have a constant electric field, you must have a positive charge, positive plate, and a negative plate. Okay, so in our case, as we have a constant field, we must have here a positive and negative plate. Okay, I don't need to put it on the graph, but you have to know the constant field is created by these plates. Here we have plus and here we have minus. Let me explain before here. If we have a positive and a negative charge, between them you have a constant field. You know, the positive charge here is the position of the high electric potential, let's say the position of the point A, and here we have the position of low electric potential, the position B. So you know, if I want to calculate V, I need to calculate the difference of potential between 2 points. So delta V between A and B equals to VB minus VA. Okay, and you know VA has a is at the position of high electric potential, so VA is greater than VB as value. In this case, this value has a negative value. Okay. Okay. Now I want to find VB minus VA. In this case, I calculate VB minus VA through this path from A to B. Okay, maybe I want to calculate VB minus VA, but through another path. This one is path 1, path 1. I want to calculate through the path AC, CB. So we can add here a point C. So we can say VAB equals VAB. You know, if we want to add two vectors, we can add a point between them. Here we have delta V AC, and here we have delta V CB. Okay, so, and here we have delta VAB. Delta VAB equals to delta VAC plus delta VCB. So we can write here delta VAB equals to delta VAC plus delta VCB. And you know delta VAC equals to VC minus VA plus VB minus VB minus VC. Okay, we can calculate like this the difference. If we come here to our problem, here we have AB. You can go directly from A to B. In this case, you have delta V AB, or we can go through a point C. So we have delta V AC plus delta V CB. In this case, we have delta V AB equals to delta V AC plus delta V CB. Like this, we can solve the problem. Okay. Okay, we come back to our problem. Here, we have the path directly between A and B. It's delta V AB. And you have A, C, CB. So delta VAB equals to delta VAC plus delta VCB. I ask you to find delta VAB through the path delta VAC plus delta VCB. You know, in general, delta V equals to minus E dot delta S. If we have delta S through x-axis, we put delta X. If it's on the y-axis, you put delta Y. Okay, so we can write, we have delta V AC equals to minus from A to C E delta. AC from A to C, it's along the Y direction. So we can write dy. Dy between A and C, it's a small portion of the displacement. So here we have dy. From A to C, dy must be directed from A to C. And E is downward. The angle between dy and E equals to 180. E dot dy equals to E dy cosine the angle between E and dy. Here equals to 180. So we can write AC E dy times cosine 180. Cosine 180 equals to minus 1. So you have minus here. So we get minus, we have minus, E is constant between at any point here in the space, E is constant. We can put E out the integral. So we have minus E integral between A and C cosine 180 equals to minus 1. So we can say minus 1 and minus you have plus. Okay, because the minus 1 here. E is out. Here we have dy. E integral of dy equals to y between A and C equals to y C minus ya. Okay, equal, y of C equals to y of B. They have the same y. Y of B equals to 0.5. So we can write, and E equals to 3 to 5. Y of C equals to y of B 0.5 minus ya equals to minus 0.3. We calculate, the value will be 0.5 plus 0.3 equals to 0.8. Here, the value is 260 volt. Okay, this is delta V AC. Okay, I calculated this one, we have to calculate delta V CB. Delta V CB equals to minus integral between C and B E dot. From C to B, we are along x-axis, so delta S must be delta X. And delta X is a small portion along the direction from C to B. We are going from C to B. Here we have dx. And you know, dx, and here we have E. E is downward. The same, this one. Okay. The angle between dx and E equals to 90. So, you know, C, B, E, dx dot cosine 90. You know, cosine 90 equals to O. So, delta V CB equals to O. We can write finally delta V AB equals to delta V AC plus O equals to 160 volt. Okay, what can we have as conclusion? Here, okay, this is the answer, okay? Let me explain one point. It means in the case of a constant electric field, it depends to the path, okay? Here we have, let's say, the same configuration. Here we have C, here we have B. So the same dimension and the same position along the plate. In this case, we have the same field, the same electric potential also. You know, delta V CB equals to O. You know, is the equipotential surface. We have the same equipotential surface. Delta V CB equals to O. V of C equals to V of B. You know, here, if you take 2 points on the plate, if we have A and B, they have the same potential, okay? Any point here, they must have the same potential, these points. We can take a rule that the electric potential is independent to the path. So we can say delta VAB equals to delta V AC plus delta V CB. This one equals to O. So we can say we can come from here to here, or here to here, or here to here. All these points have the same electric potential because they are at the same level with respect to the plate.